Now let us look at question number 4. Henry's constant in kilobar for 4 gases alpha, beta, gamma and delta in water at 298 Kelvin is given below, right. So this is the data given to us. What I personally generally do is that whenever some data is given, I just try to recall the concept. So it becomes easier for us to solve the question. First of all, the formula is that P is equal to Kh into chi. Kh is the Henry's constant, right. Second, higher the value of Kh, lower the solubility. So the solubility of delta would be more as compared to alpha. Third, when you increase the temperature, the value of Kh will increase and the solubility will decrease. So this is what Henry's law talks about. I've got all the concept. Now let us solve the question. It says density of water is equal to 10 raised to power 3 kg per meter cube. Okay, so they have used one more concept. Why they are giving this particular density? Because this particular density refers to the molarity of water equal to 55.5. Okay, that will be the molarity of water at this particular density. Okay, now let's go ahead. The pressure of a 55.5 molar solution of the gamma is 1 bar. So how do you check whether this is correct or not? So we'll say P is equal to Kh into chi. Alright. What is the value of Kh, my dear friends? For gamma, it is given to be 2 into 10 raised to power minus 5, but kilobar. So 2 into 10 raised to power minus 5. Since it is kilo, so I multiplied by 10 raised to power 3. Multiplied by chi. How do you calculate it out? What is the number of moles of the solute given over here? 55.5. So I'll say 55.5. This is the moles of solute and this will be the moles of solvent, right. So basically this 2 into 55.5 divided by this goes out or gets cancelled and you will be getting 10 raised to power minus 2 bar. So first of all, this choice is wrong because over here it is given 1 bar. But at the same time, the question is, can you apply to such a highly concentrated solution the Henry's law? The answer is no. So though I have solved it for you, but in the very first instance you would have said, sir, it is not possible, this statement is wrong. Because for such high concentrated solutions, you cannot apply Henry's law. Okay, let's go ahead. The second statement is saying solubility of gamma at 308 Kelvin is lower than that at 298 Kelvin. This is fine, this is the correct statement. Higher the temperature, lower the solubility, and that is your answer also. Still, let us look at the next choices. Alpha has the highest solubility in water at a given pressure. Now what is alpha? The value of alpha is 50. Higher the value of Kh, lower the solubility, so even this is wrong. Fourth choice, the pressure of a 55.5 molar solution. Again, you cannot apply it over here, so no need to even calculate it out. Though if you calculate, you will get the value as 250, but still it is not the right answer because Henry's law is not applicable to concentrated solution and that to such high concentrations. Okay, let's look at the next question. Question number 5. It is asking the atomic number of the element nil is. See, when you say un, it is 1. When you say nil, it is 0. When you say n, it is 9. So the correct answer is 109, which is choice number 1, right. Let's look at question number 6. An acidic buffer is obtained on mixing. Now before we go to the solution of it, let me just again write down the concept which we require to solve this. An acidic buffer requires a weak acid plus the salt of its conjugate base. The salt of its conjugate base. This mixture will give you the acidic buffer. If you want to make a basic buffer, it should be weak base plus salt of its conjugate acid. Okay. Now you have to check. Don't go on to the values first of all. First of all, check in which case you are going to get this mixture. Okay. let us start with the first one. Here we are mixing HCl with NaCl, right? You will not get the weak acid and its conjugate base. So, this is not the right answer. Okay. Second is the answer, I am skipping it. Let us go to the third one. See, here we are having the weak acid and we are reacting it with base. So, you can get the weak acid and its conjugate base, but here you have to pay attention on the millimoles over here. You see, they are same. Okay. So, you will only get the salt, that is CH3CONa, no acid would be left over here. Okay. So, even this is not giving you the buffer. Fourth case, here you are reacting weak acid plus a strong base, but dear friends, look over here, the limiting reagent is acetic acid because the millimoles are less. Millimoles of acetic acid is 10, whereas that of NaOH is 20. So, which means you will get in the solution the CH3CONa, that is sodium acetate plus NaOH, but we do not want NaOH, we want acetic acid, right. Now, the correct choice, let us write down the millimoles. Okay. So, we are mixing sodium acetate plus HCl, which is going to give us the acetic acid plus NaCl. Alright, we can leave the NaCl part. Now, how do you calculate the millimoles of sodium acetate? We are given the volume in milliliter multiplied by the molarity. So, multiply both, you will be getting 202.1, that is 20 millimoles, and for HCl you will be having 10 millimoles. So, suppose you are starting initially with this mixture, finally what is it that you are going to get? Here HCl is the limiting reagent, you will get 10 here and 10 over here and 10 NaCl, right. So, the solution is having 10 millimoles of sodium acetate and 10 millimoles of acetic acid, and thus choice number 2 is giving you the acidic buffer solution. Okay.